All right, we're going to do a derivation of Newton's laws, maybe similar to the way he did it in his day, back in the we're looking at 1700s, early 1700s. He's working on this. They already knew from Descartes and others before him had already known about conservation of momentum. Newton looked at it from another point of view. Descartes looked at it from God being immutable, but Newton looked at it more from a mechanics point of view. But we did know that, so starting with summation of pi equals summation of pf, and I believe that p is impetus. I believe that may be Newton's symbol. So we're starting with these, and the other thing that Newton, of course, Newton's second law, using it, Newton was interested in how is force involved in these, is overriding force. So the other thing was, he already knew this, F equals change in momentum over time. So that's his law. So we're going to use those two as our starting ideas and work our way down to Newton's third law, which is basically the force of A acting on B in some type of a collision is equal to, but opposite to, the force of body B acting on body A. So Newton's third law is a natural consequence of really conservation of momentum. It's more of a subset of the conservation of momentum. So let's go ahead and see how we can get there. Well, I'll start off by writing this in a little bit nicer terms. That's sort of a compact version, so let's go ahead and blow it up into the right terms. So I'm going to go ahead and say this is like mass of A times the velocity of A initial plus the mass of B times the velocity of B initial. Now we're assuming two objects hitting each other into one-dimensional, like on a railroad tracks, one-dimensional case. Now you can expand this to a two-dimensional or a three-dimensional situation. That gets kind of nasty, involving energy and involving all the cosines and sines. So we won't worry about that. We're just going to look at the general idea. And so that's going to equal the mass of A times the velocity of A final plus the mass of B times the velocity of B final. This is the instant before collision. This is the instant after collision. And the law of conservation of momentum says that momentum will be conserved. In other words, you aren't going to lose any momentum. Momentum is redistributed from one object to the other, but not lost, ultimately. Okay? So all I've done so far is take this guy and blow it up into this one down here. Okay, now there's various ways of going into this, but let's go ahead and I'm going to rearrange this, because Newton was more concerned with the change in momentum that occurred, not the overall beginning that we're all in. So let's just show this as a change of momentum. So I'm going to move, let's do it this way. Let's leave A on this side. Okay, so I'm going to move the momentum of A, the final momentum of A over here, just through algebra, subtract from both sides. And I'm going to move the initial momentum of B over to this side. So I'll subtract those parts of the equation from both sides. And I'll end up with now the mass of A times the velocity of A initial minus the mass of A times velocity of A final equals now the mass of B times velocity of B final minus the mass of B times velocity of B initial. Okay, so now I have this change, and what I really have here, we know that little p, and keeping in mind little p, the momentum is actually mass times velocity. Therefore, delta P is change in mass times velocity. Okay? So what I could say is right here, what I'm seeing is, now remember, change in means final minus initial. Final conditions minus initial conditions. So what I'm really seeing here is the negative of that. I'm seeing the opposite of the change in momentum of A, right? Because it should be final minus initial, but it's actually initial minus final. So it's the opposite. And on this side, I'm seeing, well, what I should be seeing, the velocity of B minus, so final minus initial, so that is the change in little p, little momentum, the momentum of object B. So you with me so far? A little bit of substitution, a little bit of algebra. That's what most of these derivations are. Okay, so now to get this, I want to get back up here. So if I can go ahead and divide both sides by t. Now that's legal because the time of collision, if I have two things colliding, let's say for instance, let's say this tennis ball and this orange ball, they don't have to be the same mass or anything, but if these two collide, there's going to be a time of collision. But would you agree that if the time of collision is, say, 500 milliseconds, well then it's 500 milliseconds for this and 500 milliseconds for this. It doesn't change, so the time's the same. The other thing is the time is not zero. We cannot divide by zero, but we're assuming there was some time in which they were colliding. So we can leave that. We can go ahead and divide. It's okay to divide both sides by t. Well, now you see this basically is the opposite of the force. Now, this is the change in momentum of object A, which is really caused by the force of B on A. Would you agree? It's the force of B on A caused the change in momentum of A. So this is the opposite of the force of B on A. And then this is the change in momentum of B, which is caused by the force that A put on it. So that's equal to the force of A on B. Now if you look at it, all I got to do is flip those and I have Newton's third law. So it's a, once you have your givens, it's a 1, 2, 3, 4, and then you go to that little switch there at the end. So 4.5 steps. Not a big deal, but probably be asked to do it at some point on an exam. There you go.